10.1 for geometry here, use properties of tangents. And I will warn you, we did see tangent when we dealt with sine, cosine, and tangent back with our right triangles, but this tangent is a completely different type of tangent. So if you look at chapter 10, we are talking about circles and a lot of features of circles. So this will be kind of a new chapter for us with a new shape. So let's go through our vocab first. And again, I may run through this vocab too quickly, but remember, you can always pause your video and go back and check these definitions. So our first definition is circle, which is the set of all points in a plane that are equal distance from a given point. This is an important definition because you could see this on a standardized test. And if you get this visual, if you have a point and you want every point that's equal distance, so everything that's equal distance away from that first point will create this circle. One way you can think of this, if you've ever had a pet, a goat, or a dog, or anything, if they're ever on a stake and their rope or their chain or whatever comes out, and they tend to run in a circle. It's always an equal distance. That chain or that rope doesn't change in length, and then they always go around in that equal distance, and it creates a circle. So that's a circle. The center is the point where they're all equal distance from, so you have this center of the circle. A radius is a segment that goes from the center anywhere to the edge of the circle, so that's going to be my radius. I don't know if I can get all these on with my stylus, but I'm going to try. And just a quick note for you, if there's more than one radius, we call it a radii. That's R-A-D-I-I. So just know if you see that, that's just the plural for radius. Okay, so that's the plural form of that. All right, our next one is a chord. And a chord is a segment whose endpoints are on the circle. So if I find two endpoints on the circle, that creates a chord. And notice this chord has an H in it. Your chord in music also has an H in it, but your chord, if you're talking about a kind of rope or something like that, is usually just C-O-R-D. All right, next one is a diameter. And this is also a chord, so notice it is a chord, but it needs to go through the center of the circle. So its endpoints are on the circle, but it goes through the center, and we'll call that a diameter. Then we have a secant, and this is a line, and I want to make sure you understand that one. Notice the other three we already did. Those are segments. This is a line that intersects the circle in 2 points. So remember, if it's going to go through and intersect, but it's going to keep on going because it's a line. So if it cuts through the circle, and actually that was a terrible one. Let me see if I can redraw that. I'm trying to not go through all my other points I did. Let me change colors and maybe that'll help. So I'm going to actually cut through some of my other ones. So if I start over here and I cut through the circle, okay, it comes out on the other side. That's a secant. And then finally my last one, I have the word line. It could be a ray, it could be a segment. It doesn't really matter here on the tangent. But the tangent, again, this is different than sine, cosine, and tangent. This tangent is a line that touches and intersects the circle exactly once. Well, it can't go into the circle because then it will have to come out of the circle and then it wouldn't be tangent. So it touches it exactly once. So you'll see this line just touch the edge of the circle, and that's all to be tangent. All right, so let's use some of this vocab and practice some of this. One thing I want to warn you as you go through this is make sure when you're talking about your segments and such that you label them as either a segment, as a line, as a ray, whatever it is. And just a quick note, I want to tell you right here, the center of this circle, if I was going to tell you that, it would be point. Don't forget from chapter 1.1 when we did this, that I'd have to say point C for the center because that's where it is at the center there. I also want to point out to you when you see this right here, when they name a circle, if you think about naming a triangle, we would draw the triangle ABC, whatever it is. Notice here they draw this circle with a tiny dot in the middle, and that stands for a circle. So instead of writing out the word circle, you can just draw that, and then they put whatever point is at the center. So this is circle C because the center point is C. All right, so we're looking at each of these. They're telling us, and we're going to say if it is a radius, chord, diameter, secant, or tangent. So the first one is segment BC. So it starts at B and it ends at C. Since it goes from the edge of the circle to exactly the center, this one is going to be a radius. and it's super important to remember it stops at those endpoints. Notice that could also call CB, it would be the exact same radius. Next we have line EA. I find E over here, I find A here, and I follow that line which keeps going. And because it keeps going and it comes into the circle and goes out of the circle, again it goes through the circle, this one will be a secant. And then finally our last one is ray DE. So it starts at D and it goes to E and it keeps going that way with our arrow going through the E. It looks like it touches the circle exactly once at point B there, so that will make that one a tangent. And notice this one's a ray. I could also call it line DE and it would still be tangent line or a tangent ray. Could be a segment if I just called it segment DE. So what's above it, and I do want to stress this, if you do any diameter, chord, or radius, make sure you always make them a segment. Secants need to always be lines, and tangent can be a segment, a line, or a ray, whatever it needs to be. All right, moving on to page 2. Oops. All right, on page 2, notice we have a coordinate plane here, and we have some circles on our coordinate plane. And one thing I want to make sure you to stress here is always check the scale. It looks like the scale here is 1. So since my scale is 1, each of these lines are exactly equal 1. So the first thing it says is go to circle A. Notice I have circle A here. And find A as the center, and I want the radius. So that's how far from the center out. Now I could draw a radius like this, but I'd have to use some distance formula and have to know that. Make sure you take the easy route. Go from the center and go either straight up, straight down, straight to the right, straight to the left, something like that. And it looks like it covers 2 lines or 2 units, so that's the radius. A diameter always equals twice the radius, so 2 times 2 here. And I have a radius, or a diameter, sorry, of 4 for circle A. When I go to circle B, I have from B, and I go all the way out. That's the center. I'm going to go all the way out, and I count the spaces. That looks like 1, 2, 3, 4 spaces. So my radius is 4, and my diameter is going to be twice that. So my diameter is 8. And again, just be careful because if the scale is different, we're going to need to change the lengths of those. All right, moving down to the bottom of the page. Maybe. All right, so it comes back on number 1 here, and it says, looking at example 1, and that was on the first page, and it says segment AB. Just to give you a quick reminder, in the circle of page 1 there, A was at the top of the circle, B was exactly at the bottom, and just so you know, it happened to go right through C. And because it went through the center C, we know AB is a diameter. And I guess I already had that typed, so it gives you a quick answer on that one. AB is a diameter because it's a chord that contains the center C. Quick side note here, if you're asked to name a chord, you may name a diameter as the chord or any other segment as a chord. So just know that diameters can have 2 names, both diameter and a chord. All right, on number 2 down here, I'm going to do this, and I know it's not there, but I'm going to change it just to kind of give you this warning in case you get that later. I'm going to change all these lines to 2. I just want you to get used to if your scale is not 1. All right, so we have the job here we're looking at is we're going to find the radius of C. So A is going to be the radius of C. And then B is going to be the diameter of D. Okay, so starting with the radius of C, circle C here is here, and we go just straight from the center out to get the radius. There are 3 spaces, but because each of the 3 spaces are number of 2, my radius would be 6. For D, it's easiest to go with the radius here. My radius is 1, but each of those lines is actually 2, so it's 2. So my diameter is going to be twice that, so 2 times 2 will be 4. So make sure that you pay attention to the scale of those graphs. All right, moving on to page 3. So I have Common tangents. Make sure you copy down this definition from the margin because it's super important to know what a common tangent is. On a common tangent, we need to talk about more than one circle. Typically, we talk about two. And on this common tangent, I'm looking for lines that intersect both circles at the same time. Now, remember, a tangent, though, can only touch the circle once. So when I take a line, it needs to touch both circles, but only once on each circle. So sometimes it's easy to see a common tangent on A here. I can take this outside one. There's one of my tangent lines. I can have another tangent line here. Let's pretend it touched there because I can't get my stylus to go right where I want it. So there's two lines, but don't forget I can get one more tangent line right between here. So if the two circles are touching, I get exactly 3 common tangent lines. B gives me another scenario where I have 2 circles that are overlapping. And so I have a common tangent line. I can't get in between them this time, but I can get one on the outside here, and I can get another on the outside here to give me 2 common tangent lines. So remember, a tangent line touches a circle once. The common tangent touches both circles exactly once. For C, my next scenario has a circle inside a circle, but they're touching. I can get 1 common tangent line. That didn't even come close to hitting. Let's see if I can try that one again. 1 common tangent line right there. It touches each one of them once, so I get 1 common tangent line. You'll notice for 3 and 4 down here, they just keep going, and I get 2 more scenarios. On 3, I have 2 circles. One is inside of each other. I cannot touch that inside circle without touching the outside circle at least twice. So because of that, I have 0 common tangents. Okay. Tried cursive. I don't know if that's easier or not. And the last one on 4 here. I have 2 circles. They're not touching. So I'm going to try to do as many common tangent lines as I can. I have, wow. I'm going to tell you here that precision is not my best with this stylus. I have 1 line here. Let's pretend it touched both of them. I have a bottom line here. Let's pretend it didn't go through that one. And then we have these other lines that actually come through each one of them that touch each one once as it goes through kind of the centers. And again, I'm going to apologize that I can't do a more accurate drawing there. So I actually get 4 common tangents here on number 4. All right, our first theorem here in chapter 10 is in a plane, a line is tangent to a circle if and only if the line is perpendicular. I guess this would have been a good time for my symbol of my upside down T. Perpendicular to the radius at the circle at the end point. So when I have a tangent line and a radius, I always get a perpendicular or right angle. And I'm going to tell you, this is a super important one, and it's one that we tend to forget a lot, and it's one that we really need to remember, that a tangent line is always perpendicular to the radius that comes out to that same tangent point. So we will see that property quite a bit, and we're going to use it here on the next couple pages. So let's move on to page 4. All right, so on page 4 here, at the top on example 4, it says, in the diagram, RS is a radius of circle R, and it asks, is ST tangent? So the one thing we know is if ST is tangent, we should have 90 degrees right here, which would make a right triangle. So then RS would be perpendicular to TS. And if that's the case, we should get a little a squared plus b squared equals c squared. Ran off the side of my page. So let's go ahead and do a little math here to see if this will work. They kind of set me up right here. I'm going to set it up in the margin so I can have a little more room to do this. Remember when we do Pythagorean Theorem that our C always needs to be our hypotenuse or our longest side. So we would really like S here to be the right angle, so we would like our C to be 26. So let's put 26 in our C, and then our 10 and our 24 can go in the other 2 positions. All right, 10 squared here is 100. 24 squared is 576. And 26 squared is 676. When I add these two together, I get 676 equals 676. Since this is this, which means I have a right triangle, and that means that I have a tangent line because I have a right triangle or a perpendicular lines there. So let's go ahead on number 5 and number 6 and check to see if these are also tangent lines with the same type of math. Now, one thing I want to warn you about on number 5. This 8 is only measuring from the edge of the circle out to T. So how long is it from R to T is the question. Well, I have a circle, and this measurement from R to S right here is 5. Another name for that measurement is a radius, and we know every radii in that circle is the same length. So if this is 5, R to the edge is also 5, so that means R to T will be 5 plus 8, which will be 13. Once again, if this is a tangent line, I really want S to be that 90-degree angle. So I'm going to check with a little a squared, b squared, c squared again. And this time I want my C to be my longest side, or my 13, and I'm hoping it's across from my S. So let's check our numbers and see if they'll work on this one. 5 squared is 25. 12 squared is 144. 13 squared is 169. And 25 and 144 make 169. So once again, I have an equal, and because I have an equal, then yes, this is tangent. All right, so let's check number 6 over here. Again, they kind of pull the same thing they did here. 12 is my radius, so I'm going to add 12 in here. So my entire side for RT here is 19. And hopefully I can keep this on my paper. So again, I'm hoping S would be where my right angle is, if there is one. Looks like my C would be this 19. And it doesn't matter which is 16 and 12 as long as they're there. So 16 squared is 256. 12 squared is 144. And 19 squared is 361. When I add 256 and 144, I get 400. And 400 does not equal 361, so that means I do not have a right angle. And if I don't have a right angle, then ST is not tangent. All right. Let's move on to example 5 here. All right, on example 5, let me switch my pen color once again. In this one, they tell me that B is the point of tangency. So as soon as I know that, I can write a right angle in there. I don't have to check it. I know it is a right angle. This time they want me to find the radius of C. So once again, I have a right triangle. I still like to do a squared, b squared, c squared. Just so you know, they kind of mixed it up here and they put the c squared first, which is always fine. And we're going to plug in here. Now, I need to find my C. It's always across from my right angle. And so it's this side over here. Right now I have 49 and R. How do I join those together to make my full hypotenuse? Now, I commonly hear people tell me, well, that's 49R. Well, be careful. If R is 8, you don't want to do 49 times 8, and that's what 49 times R or 49R would be. I would want to do 49 plus 8 to get the full thing. So remember, we're adding these two pieces, okay? So I'm going to do 49 plus R for that whole length. Okay, and just so you know, you can flip that around and make it R plus 49. It goes either way because it's commutative. I can write it either way. That is my C, so you'll notice they put it in the C spot. And for my A and my B, I just need R in 1 and 77 in 1. And of course, they didn't give me very pretty numbers. All right, I need to remind you here some algebra. If I have R plus 49, and I'm going to square that, whoops, I'm going to square that. That means I'm taking R plus 49 times itself, R plus 49. And whenever I see two binomials like this, I need to remember to FOIL. Okay, so what that's going to do is give me first times first, that's my f, r times r is r squared. Then I'm going to do my o, which are the outsides, r times positive 49 is plus 49r. Then I'm going to do my insides, which are 49 and r inside, and that gives me another plus 49r. And finally, my lasts are my 49 times my 49. And hopefully you have a calculator handy. I think that's 2,401. And no, I did not do that in my head. I already wrote it down, so I didn't mess this up. All right. So on my left side, when I combine all this and do like terms, I get r squared plus 98r plus 2,401 on my left side. On my right side, r squared is just r squared, and 77 squared, again, a calculator would be handy, is 5,929. All right, it's time to solve this. We like terms together, so if I try to get my r squareds together and I subtract r squared from both sides, thankfully for us, they cancel. So I'm going to be left with 98r plus 2,401 equals 5,929. I only have one r left, so I'm working to get it by itself. So I'm going to leave my 98r on the left. I'm going to subtract 2,401 from both sides, and I get 3,528. And I need to divide by 98 yet. And I'm going to find a radius of 36. Now, quick note, they did not give us pretty numbers, but it worked out. I just want to give you a hint. Sometimes you don't get pretty numbers, and sometimes your radius will be a decimal. But I can't stress enough the problem. The biggest mistake people make in this problem is forgetting to FOIL. When they get to this over here, you have to remember to FOIL, or else your r squareds will cancel and you'll have nothing left. If you don't FOIL, you don't end up with this r term in the middle, and that's where the biggest mistakes come from. So make sure you remember to FOIL. All right, moving on to page 5. I think we're going to try another theorem here. And this theorem is about tangent segments. It says tangent segments from a common external point. That means if both tangent lines come from the same point. So I have this line that's tangent to the circle, hits it once, this one here. And by the way, these are segments. They're stopping right when they hit the circle. Common external point, these tangent segments will be congruent. So if they both come from the same position, they will both be congruent. Okay? So in example 6, QR is tangent to the circle C at point R. QS is tangent to circle C at point S. We're going to find the value of X. I have one point. They're both tangent lines, and because of that, these two segments will be congruent. So QR is 32. QS is 3x plus 5. And I'm going to solve here for x. I'm going to subtract 5 first and get 27 equals 3x. Divide by 3, and x equals 9. So common tangent lines or tangent segments from a common external point will be congruent. All right, moving our page up here. Maybe. All right. My next one here, number 7, looks similar to the problem we ended the last page with, so it looks like we're going to be looking at a little a squared, b squared, c squared again. As soon as I know that I have a point of tangency, go ahead and put that little right angle right there. That'll help us to know that we can do some a squared, b squared, c squared. So I'm going to do a squared, b squared, c squared again. Every right triangle can use Pythagorean Theorem. And again, I need to be careful. My c is across from my right angle, and I'm going to call this r plus 32 to get the full length. So my a can be r, my b can be 56, and my c can be r plus 32. Make sure you put the parenthesis around there, and we're going to square it, which means once again I'm going to FOIL. I'm going to come over here in my margin for a little more room, r plus 32 squared. So that means I'm taking r plus 32 times r plus 32. And I'm going to FOIL again. First r times r is r squared. O is my outside, so r times positive 32 is positive 32r. insides are the two inside here, positive 32 times r gives me another positive 32r. And finally, my last two is positive 32 times positive 32. Calculator's handy here to get 1,024. All right, so on my right side, I'm going to simplify that down to r squared plus 64r plus 1,024. On the left side, r squared is r squared, and 56 squared, calculator help there, 3,136. Once again, my r squareds are going to cancel. I'm going to get 64r here. I'm going to subtract 1,024 from both sides. And when I subtract that from both sides, I get 64r equals 2,112. Divide by 64, and r is going to equal 33. So once again, big numbers. Thankfully, we had a calculator handy. And I think your homework has a little bit smaller numbers. But don't be afraid if you get a decimal, but make sure you remember to do that foiling. All right, last example on here before we turn the page, because I do have some special ones on the back. I have RS is tangent to circle C at point S. RT is tangent to circle C at point T. That means I have one common external point that goes to two different tangent points, which means these two are equal. So that means that my x squared is going to equal my 49. To solve for x, I'm going to take the square root of both sides, and I get x equals 7. Don't forget it could be plus or minus 7. I'll do a check just to make sure it works. If I plug in positive 7 and square it, I get 49. If I plug in negative 7 and square it, I still get 49. So technically on this one, both answers will work. So I'm going to get two answers there instead of just one. Always double check. Sometimes you'll get two answers and one of them won't work. So always double check those. All right, and we are ready for the last and final page on number 6. Yeah, forget what I'm doing again here. All right. I have L and M are tangent circles. So if they're tangent circles, it means they're touching right in one spot to each other. So just like a tangent line, tangent circles touch at one point. And JK, that line there is a common tangent line. So it's touching each circle exactly once. Because it's a common tangent line, I'm also going to go ahead right away and throw those right angles on both of those, because we know that when the radius hits the tangent line, we make it perpendicular. Our job today is to find the length of JK. So from J to K, what is that length? All right. We can stare at this one for a while sometimes and it looks pretty scary. So I'm going to kind of give you some hints here. So we have these radii that are already marked in length. I want to draw this line from L to M. So I have tangent circles from L to M. If you think about this, from L to the edge of the circle is 10 because it's a radius. From M to the edge of its circle is 4. So this whole line here from L to M is 14 when I use my two radii together. But I'm still trying to find X over here. Now, quick note, because both of these are right angles, we know that JL and KM actually are parallel to each other because they're both perpendicular to the same line. So going back to a chapter 3 note, we know they're parallel to each other. So we have a trapezoid going here. We don't have a rectangle. That would have been a lot nicer, but we have a trapezoid here. I'm going to go ahead and draw another line for us. You're always allowed to draw extra lines in pictures. Sometimes they help, sometimes they don't. I'm going to draw this line right here. Oops, not even close to where I want it. About right there. And by the way, I'm going to make it right angles here. Turn my mistake into a right angle. So I've drawn this extra line in my trapezoid. Notice, because I made it right triangles, that I've actually created a rectangle. So I'm looking for this X up here. It's also going to be my new line right here, this red line. If my radius over here is 4 and I have a rectangle, its opposite side also has to be 4. So this is going to be 4 just down to where this right angle maps. And believe it or not, this picture may not be drawn to scale, so don't trust the picture, trust the numbers. If the top part of my radius is 4 and the full part of my radius is 10, that leaves me 6 for the bottom here. If this is a right angle here, it also will be a right angle to finish out this line. So now what you see is I have my trapezoid and I've divided it into a rectangle on top, but what that leaves me on the bottom is a triangle. And nice for us, it's a right triangle. Let me redraw it here. I have 6 here. I have 14 on the bottom from L to M, and I'm trying to find this X on top. There's my right triangle. I can use a little a squared, b squared, c squared to find my missing side. Now, always know which side's your longest. Since I'm missing one, I don't know what its length is, but I do know where my right angle is, and across from my right angle has to be my hypotenuse, which is my C. So that gives me 14 for my C, and I can mix or match my 6 and my X for my A and my B. 6 squared is 36. 14 squared is 196. I can subtract my 36 here, and I get 160. And my last and final job is to take a square root here. And just so we know, this is not a whole number. Square root of 160, a little calculator help on that. And I will get 12.6. So if my length on this side is 12.6, then J to K will also be 12.6. All right, ignore this homework from the book. I'm going to give you a worksheet instead. So thank you for following these notes today. Again, try to do your best on either putting them into printing out my blank notes or getting a new note piece of paper and taking down the most important things. And remember, you can always come back and rewatch these notes. They're going to be online for the rest of the semester, so come back as often as you want to look at these examples or watch these notes.